This is day 17 of Unit 5. So we started today with this warm-up. So pause the video, take a moment and try it, and then play to check your answers. So here's the warm-up. So we take, first of all, we use Pascal's triangle. Up to row 4, and we use those numbers to get the coefficients 1, 4, 6, 4, 1, and then we just take the first term 3m to the first power of 4, and then it's to 3, then it's to 2, then it's to 1, then to 0, and then the negative 2n goes to the 0 power, and then to the 1 power, the second power, the third power, and the fourth power. So then we just simplify and multiply. So 3 to the 4th is 81, m to the 4th. 3 cubed is 27, m cubed. Next step, I'll multiply that all out. 3m, the quantity squared, is 9m squared. Negative 2n, the quantity squared, is 4n squared. Again, I'll multiply that out in the next step. And here, negative 2n, the quantity cubed, gives us negative 8n cubed. And negative 2n to the 4th power gives us positive 16n to the 4th. So when I multiply out the 4, the 27, the negative 2, I get negative 216 m cubed n. 6 times 9 times 4 is positive 216 m squared n squared. 12 times negative 8 is negative 96 m n cubed. And lastly, plus 16 n to the 4th. So that's your final answer. So today we started by looking at the rational root theorem. So you'll need to copy that theorem into your notebook, and also example number 1. Now, before I talked about what the rational root theorem says and how we use it, I really just reminded you of where we left off before break. We were finding the roots. And what happened before break was I gave you the first root and then you use synthetic division to get the rest. Well, eventually our goal is to find all of the roots and then to graph the polynomial without being given the first root and without a calculator. So eventually I'll give you this polynomial here and I'll ask you exactly that. I'll ask you to graph it without using a calculator. So the rational root theorem is going to help us to get a list of possible rational roots so that we know what values to try to be possible roots to try in synthetic division. So that's where we're headed with this. That's what we're going to use the rational root theorem to do, or to help us do. So now let's talk about what it says. So I'm supposed to find the factors of p, where p is the constant. So p is this number on the end. Now, when I'm figuring out the p and the q, I disregard the sign. So I'm really just concerned with the 24, not the negative. So I'm looking for the factors of 24. And I'm supposed to put them divided by the q. So this is our p. The q is the leading coefficient, which is a 2. So I'm supposed to divide that using the rational root theorem. I'm supposed to divide that by the factors of 2. So when we're talking about factors, keep in mind it could be a positive times a positive, but it could also be a negative times a negative. So not only is 1 and 24 are 1 and 24 factors of 24, but so is negative 1 and negative 24. So to indicate that they could be positive or negative, you're just going to put plus or minus and then parentheses, and you'll list all the factors and then end the parentheses. So factors of 24 we know are 1, 2, 3, 4, 6, 8, 12, and 24. And again, I put that parentheses around it and plus minus in the front. And then I'm going to do the same thing with the factors of 2. So plus minus parentheses 1 and 2 are the factors of 2 and the parentheses. So now what we need to do is we need to simplify this so we have our final answer, our final list, our final p over q. So we have plus minus. And then we have each one of these numbers divided by 1. Well, each one of these numbers divided by 1 gives me each one of those numbers. So 1, 2, 3, 4, 6, 8, 12, and 24. They're all on the list of possible rational zeros. Now I need to take each one of those numbers in the numerator and divide by 2. And if it's already on my list, I'm not going to add it. But if it's not on the list, I will add it. So 1 divided by 2, 1/2. that gets added to the list. 2 divided by 2, that's 1, so it's already on the list. 3 divided by 2 is not on the list. 4 divided by 2 is 2, 6 divided by 2 is 3. You'll notice the rest of these, 8 divided by 2, 12 divided by 2, 24 divided by 2, they're all already on the list. So now my list is complete. I'm going to put the end parentheses, and the possible factors that are the possible rational zeros from this polynomial equation are this list. So all of those numbers and all of those negative numbers are possible rational zeros. Now, I just want to point one other thing out. I underlined rational because I just want you to realize that this theorem, this list here, is only the list, excuse me, of possible rational zeros. So if this polynomial has zeros or roots that are complex or that are irrational, like let's say the square root of 3 is a root, or 2 plus I is a root, they're not going to show up on our list. Okay, this list only includes the real rational zeros, or the possibilities for real rational zeros. So no irrational will show up on the list, and no complex or imaginary roots will show up on the list. But it will give us all of the possibilities for positive or for real rational roots. Okay, so take a moment, copy this one, and then give the rational root theorem a try. Pause the video, try it, and then play. So if I'm checking that with rational root theorem, I'm looking at 10 and 3. So factors of 10, ignoring that negative sign, divided by the factors of 3, give me plus minus 1, 2, 5, and 10, divided by plus minus 1 and 3, which gives me plus minus 1, 2, 5, and 10. All of those are divided by 1. And then all of those divided by 3 gives me 1/3, 2/3, 5/3, and 10/3. And that is my list. Okay, so that's the rational root theorem. Next, Descartes' rule of signs. So go ahead and copy this example into your notes. Now, Descartes' rule of signs gives us different information. It'll tell us how many positive roots there are and how many negative roots there are for a polynomial equation. So what we'll do, Descartes' rule of signs says you're going to take your function f of x and you're going to count the number of sign changes. So here's what I mean by that. It starts off with a positive 2 and then it goes to negative. So the sign change there was positive to negative, so that's one sign change. And now I need to continue through the rest of the polynomial equation. So negative to negative, no sign change. Negative to negative, no sign change. So because there was one sign change, that means that there's going to be one positive root. Okay, so there's going to be one positive root because of the one sign change. So now what we're going to do is we're going to find how many negative roots there are for this polynomial. So to do that, what we have to do is we have to find f of negative x. F of negative x. And so if you recall, we talked about that earlier. That's just function notation. That means I'm going to substitute negative x everywhere I see an x in the function. So that means 2 times parentheses negative x, the quantity cubed, minus in parentheses negative x, the quantity squared, minus 22 in parentheses negative x, and then minus 24. Well, of course, I have to simplify that. So when I cube a negative, negative times a negative times a negative is a negative. So it's going to give me a negative x cubed. Well, negative x cubed times 2 is negative 2x cubed. Remember, order of operations, exponents come before multiplication. So I square negative x first, and negative x times negative x is positive x squared. Positive x squared times negative 1 is a negative x squared. Next, negative 22 times negative x gives me positive 22x. And last, minus 24 is on the end. So if I'm checking f, now I need to look at f of negative x, which is what we just found, and I'm counting the sign changes. So a negative to a negative, that's not 1. A negative to a positive, that is 1. A positive to a negative, that makes 2. So there are 2 sign changes. Okay, so here's what happens. We didn't have to do this with the last one because there was only one sign change. But when there's a number, when this number of sign changes is bigger than 1, you first of all include that as a possibility. So I could have 2 negative roots. But I then have to take that number, 2, number of sign changes, and subtract 2. So I'm going to subtract 2. 2 minus 2 is 0. So another possibility besides 2 would be, or I could have 0 negative roots. Okay, so I could have 2 negative roots, or I could have 0 negative roots, no negative roots at all. And I keep doing that. I keep subtracting 2 from my original number, my number of sign changes, until I reach 0 or until I get to negatives. I want to stop when I get to negatives because you can't have a negative number of roots. So I have either 2 or 0 negative roots for this polynomial. Now, again, I didn't do that with the positive because 1, I can't subtract 2 from without going into the negatives. So there's only one possibility. It definitely has 1 positive root. But we have 2 possibilities for the number of negatives. There's either 2 negative roots or there's 0 negative roots. Now keep in mind, if there's 0 negative roots, but it's degree 3, we talked earlier in the unit about the fact that there'd be 3 total roots. Well, if there's only 1 positive and there's 0 negatives, that still leaves 2 roots because we know there's 3 total. 3 total roots, only 1 is positive, and we don't have any negatives. That means that the other 2 have to be complex. Okay, and again, we'll talk way more about this later as we progress throughout the rest of the unit. But just keep in mind, I have definitely 3 roots. So if I have 1 positive, I could have either 2 negative roots or no negative roots. And in which case, if I have no negative roots, then that means the 2 roots that are left have to be complex. Okay. On the other hand, if I have the 1 positive and the 2 negative roots, then that takes care of my 3 total roots, and there would be no complex roots in that example. Okay, but that's how Descartes' rule of signs works. So we count the number of sign changes for the original. That tells us the number of positive roots. Again, you'll take that number of sign change and keep subtracting 2 until you get to 0 or a negative number, and then you stop. Same thing for the number of negative roots, except for we want to first find f of negative x, simplify that, count the sign changes, and once again, that number, and then keep subtracting 2 to get all of the different possibilities for the number of negative roots. So we talked about some for instances in class. I said, well, what if I counted the sign changes for f of negative x and got 4? In which case, 4 would be a possibility for the number of negative roots. 4 minus 2, which is 2, would be a possibility for the number of negative roots. And 2 minus 2 is 0, would be another possibility for the number of negative roots. So if I got 4 sign changes when I found f of negative x, that would be either 4 or 2 or 0 negative roots. Okay. Similarly, let's say 3 sign changes. Well, 3 or 1 would be my possibility because 3 is the number of sign changes I found. Minus 2 gives me 1, and then if I try to subtract 2, I'm going into the negatives. So it's either going to be 3 or 1 negative roots. Okay, we did one more example here. So you probably want to copy this and pause the video and then try it. So let's first find the number of positive roots. So positive 3 to negative 22, that's 1. Negative 22 to positive 37, that's 2. And positive 37 to negative 10, that's 3. So that means either 3 or 1 positive root. Okay. Now I'm going to find f of negative x to help me figure out how many negative roots there are. So f of negative x means 3 times negative x, the quantity cubed, minus 22 times negative x, the quantity squared, plus 37 times negative x minus 10. So when I cube negative x, I get negative x cubed times 3 is negative 3x cubed. Negative x squared is positive x squared. Negative x, the quantity squared, is positive x squared. Positive x squared times negative 22 is negative 22x squared. Positive 37 times negative x is negative 37x, and then minus 10 on the end. So negative to negative to negative to negative, there are 0 sign changes. 0 sign changes for f of negative x means that there are 0 negative roots. That you will find as we do more of these problems and as we actually continue on and do the graph, that's very helpful information right there. If we know that there are 0 negative roots, think about it. If I'm starting a problem from beginning to end and I want to end up with a graph, and I do the rational root theorem first, so I already have my list of p's over q's. I have that long list. Remember, it has plus minus in the front. So all those numbers on the long list and all those negative numbers on the list, I have to try using synthetic division, hopefully to find a 0 remainder so that I know it's a root. Well, if I also do Descartes' rule of signs, which will do both, rational root theorem and Descartes just told me that there's 0 negative roots. So basically what just happened is that long list that I got from rational root theorem just got cut in half, because I know I can disregard all the negative roots, all the negative possible roots, and just focus my attention on the positives. Okay, so that is really useful information, or it will be later once we start graphing these. For now, you're just going to use Descartes to find this, to find the number of positive roots and the number of negative roots, and you're going to use rational root theorem to figure out the list of possible rational roots. So your homework is all of worksheet number 4 in Unit 5. And then you'll see on worksheet number 5, there's problems where you're asked to do the graphs. You're not doing that yet. First of all, you're only going to do problems 1 and 2. And in those 2 problems, 1 and 2 on worksheet 5, you're just going to do the rational root theorem. So get that list of p's over q's and Descartes. And that's it. You'll stop. You're not going to do a graph. You're not going to do anything else. You're just using rational root theorem and Descartes for problems 1 and 2 on worksheet 5. You're going to do all of worksheet 4. Okay, do that for tomorrow. Keep in mind, please, that our schedule's a little bit off because of the snow. So everything got pushed ahead a day. So we're just a day behind in our calendar.